Thanks a lot. Yeah, thanks for that introduction, and thanks a lot for having me here. I'm really happy to be here. So yeah, today I'm going to be talking about data-driven and data-augmented modeling of chaotic spatiotemporal dynamics for applications in geophysics and fluid dynamics. The title is a bit of a mouthful, but I like to have a descriptive title. So yeah, just to introduce. Sorry, go ahead. All right, assuming you can still hear me, okay. To introduce the topic, the modeling, the state of a fluid dynamical system is important for many scientific applications, such as numerical weather prediction and climate modeling. But this is a difficult problem due to the mathematically chaotic nature of turbulent fluid flows, which lead to a hierarchy of interacting scales. And so yeah, you have small scale interactions affecting large scale interactions, and vice versa, and everything's chaotic. So it's difficult to predict the state of a fluid dynamical system. So in this talk, basically, I'll be talking about two main topics. In the first part, I'll be talking about purely data-driven machine learning based modeling. And in the second part, I'll be talking about data-assisted or hybrid modeling. So the first part mainly deals with just using machine learning as a black box. So you purely learn from data, and as I'll show that you can go pretty far with doing just this. But in part two, I'll lightly touch upon the topic of data-assisted or hybrid modeling, in which you combine a machine learning model with some with a numerical physics-based model, and see what the combination of the two approaches can do together. So yeah, let's talk about purely data-driven machine learning models. So purely machine learning-based models attempt to create a mapping between the history of some flow field to the future. So this is just a cartoon illustration that I'm showing here, where you have a set of historical states, and you have a machine learning model that's trying to create that's trying to learn a map from data between the historical states and the future states. So it's going to take some sequence of steps x of t minus k tau, x of t minus tau, up to x of t, which is the present time step, and use a machine learning model to output the future state at some time in the future, t plus tau. And in this case, the machine learning model has to learn a time stepping function, and such machine learning models that need to learn spatial and temporal dependencies together can be difficult to train at scale, as we shall see in a few slides. So what happens is that the computational cost of training pure machine learning based fluid dynamics models can be prohibitively high for all but the simplest of problems. For instance, there's been a lot of recent work on, and which shows a number of impressive advances in the development of data-driven models of the Earth's atmosphere. But the question still remains is that can these models match the accuracy of state-of-the-art physics-based general circulation models, which are typically used for numerical weather prediction, for generating your weather forecast that that we all know and use. So the story sort of starts at a very sort of simple place, where we showed way back in 2018 that we can forecast the short-term state of a chaotic dynamical system, namely the Kuromuro-Sivishnsky system, by using a simple neural network, which has been just trained on data. And what we showed there was that we can, and what you see in the figure here is that if you have a machine learning model that's been trained on historical data from the Kuromuro-Sivishnsky system, then given a new initial condition, it can predict the state of the Kuromuro-Sivishnsky system, which is a chaotic dynamical system, for a really long time in the future. And when I say really long, I mean compared to the natural time scale of the system. So in this case, the natural time scale of the system is defined by the Lyapunov exponent of the system. And what we see here is that your machine learning model, which has been trained on data from the system, can accurately forecast the system for up to 5 multiples of the Lyapunov time. And this is significant because if it was if it was a fraction of a Lyapunov time, then you can have a fairly linear model that can achieve that. But when you're talking about multiples of the Lyapunov time, then you need a model that truly learns nonlinearities that are inherent in the system, and is also stable under chaotic dynamics to be able to forecast that far into the future. So that's really nice. That's a simple toy model, one-dimensional system. Let's see what we can do next, which is basically what if you go to a very high-dimensional system? So if you go to a high-dimensional dynamical system, so the attractor dimension is really high. Then what we found out was that if you parallelize your neural networks, and you basically add a lot more computing power. So basically, each of these neural networks is so you break up your domain into small bits and pieces, and then you train an independent model on each segment of the domain, and then you have these segments interact with each other through MPI parallelism. And then what happens is that if you have effectively what you're doing is just giving it a lot more computing power. So each of these neural networks has been independently trained, and it has been trained on a single CPU core. And so what we do here is that we train the model on hundreds of CPU cores. So effectively your model size and the expressivity of the model has gone way up. And if you do that, then you can forecast even very high dimensional or arbitrarily high dimensional chaos. Still one spatial dimension, but basically what we can show is that using parallelization, you can scale techniques that work for you in low dimensional dynamical systems to even higher dimensional dynamical systems.
Can I interrupt for a minute? Can you just explain how the input is going?
Yeah, definitely. So what we're doing here is that we have a one-dimensional domain, right? I mean, that's indicated by the indicated on the bottom of the figure, essentially. Sorry, I can't really get my cursor to work on the screen, unfortunately, but I can't really mouse over here. But the bottom of the domain is of the model is where you're feeding in your input, right? And then at the top is the output. So you have each of the highlighted recurrent neural networks basically is getting inputs from a subset of the domain, and it's forecasting a smaller subset of that domain, essentially. Does that make sense?
It's an extended system, right? So each one of the input nodes is getting input from a different segment of the active system. Is that how it is?
Yeah, this is a one-dimensional grid, essentially. So the one-dimensional grid is divided into smaller segments, which are on which you train independent recurrent neural networks. Yeah, we can come back to this point later, but so effectively, you can have a larger neural network which uses a lot more computing power, and you can use that to train high-dimensional dynamical system, train machine learning models that can forecast high-dimensional chaotic dynamical systems. And so what we did after that was, can you use this for can you train these models on general circulation models? Basically, these are systems.
Sorry, one quick question. Can you go back to the previous? So the bottom thing is, you said true physics-based model. What exactly is the panel D?
Panel D is the true physics-based model. So basically, you have a Kuromurov-Sierpinski system. I mean, you give the same initial condition to both the machine learning model and the exact dynamics, so the exact PDE solver that was used to create the training data, right? So like C and D have the same initial condition. They're just C was forecast using a machine learning model, and D was forecast using by solving the actual PDE. And they both have very similar errors. So that's what's impressive about this.
So I mean, sorry, I'm a bit lost. Isn't that A minus A? So 0. I mean, A is the ground truth.
Yep.
And B is the machine learning prediction.
Yes, that's B minus A is C.
So B minus A is C. So what's D?
Yeah. D is you basically initialize your PDE forecast using the same initial condition that was used to generate the machine learning prediction.
And so is D basically just numerical errors? I'm a bit, if it's a deterministic model, it should give you the exact identical for all times, right? And,
Right. So what happens is that there is some error in the initial condition, basically. So we start with the first step of the machine learning model, essentially. So that error gets amplified due to the chaotic dynamics. That's why it's exponentially increasing over time.
Okay. Yeah. Thanks.
Yeah, and then we basically try to extend this to a general circulation model, and the concept is the same. It's still the same neural network architecture with reservoir computing, and what we do is basically divide the two-dimensional domain in this case with a similar domain decomposition strategy. And along with our collaborators, what we showed was that the parallelized ML configuration that we introduced for a toy model can be used to emulate the full state vector of certain variables of a global atmosphere in a simplified circulation model with a forecast scale comparable to the physics-based model out to 4 days. And these plots basically just show the northern hemisphere temperature at the RMSE in the northern hemisphere temperature at 24 hours, 48 hours, and 72 hours. And yeah, I mean, we can beat persistence fairly solidly, and then the model is pretty comparable to the actual physics-based model forecast. And this is on a simple, again, this is on a simple general circulation model called SPEEDY. It's it's not quite an operational model. It's just basically a research model. But that's pretty promising that you can do that with a machine learning model. And this was in 2020. But now let's look at high resolution numerical weather prediction surrogate ML models. So all this prior work that we've shown has been focused on either toy models or creating surrogate weather models trained on fairly coarse low resolution data. And that's mainly due to neural network architecture limits and computational cost limitations. So what we've been doing recently has been attempting to create a high resolution surrogate weather model that can be directly compared to operational NWP models. And so the way we train these models is, we use a high resolution. We use basically a data set that's put out by the European Center for Medium Range Weather Forecasting. They provide this publicly available comprehensive data set called the ERA5 data set, which consists of hourly estimates of several atmospheric variables at latitude and longitude resolution of 1/4 degrees from the surface of the Earth to roughly 100-kilometer altitude from way back in 1979 to the present day. So this is a huge amount of data. And basically on the left is an illustration of the data set. What it looks like, you have some surface winds at the top, and then you have some 1000 HPA level winds, and you have some geopotential heights at 1000 HPA. Again, you have some 850 HPA level wind velocities, U and V. Then the geopotential heights at 850 HPA, and then 500 HPA, 50 HPA, and so on and so forth. And then you have and yeah, in addition to these variables, I mean, we have a total of 20 different variables in our model, but let's get to that in a second. So what ERA5 is it's an atmospheric reanalysis data set. So what reanalysis does is that it's a combination, it's an optimal combination of observations from various measurement sources and the output of a numerical model. And then you combine these using a Bayesian estimation process called data assimilation. And then effectively the data set is a deconstruction of the observed history of the Earth's atmosphere. If we use this, the reanalysis data set, the ERA5 reanalysis data set to train our surrogate weather model. And while the ERA5 data set has several prognostic variables available at 37 vertical levels with an hourly resolution, that's a lot of data. I mean, that's a whole lot of data over 40 years. So we have some computational and data limitations along with some other operational considerations. So for training our deep learning model, we're going to restrict, we're going to basically choose a subset of these variables to train our model. So specifically, we choose to focus 20 variables from the ERA5 reanalysis data set. So most of these are wind velocity, meridional and zonal components. And there's geopotential heights. There's some temperatures, and then some surface variables and some humidity variables. But yeah, there's 20 chosen variables and 40 years of training data sampled at 6-hour intervals instead of 1-hour intervals, because when you work with 1-hour intervals, that creates a prohibitive amount of data and to train the model on. So like for this initial first set of experiments, we trained on 6-hourly subsample data. And I'm not going to spend too much time on the architecture of the model, but I refer you to the paper which was published which actually accepted at ICLR recently by some of my colleagues. This was written by my colleagues. I wasn't involved in this paper directly, but I definitely encourage you to check it out. But yeah, so basically, this is a transformer-based model. You have as inputs to the model, you give it a whole bunch of channels, which are basically prognostic atmospheric variables, and the input is some the state of the atmosphere at time t, and the output is the state at time t plus delta t, where delta t is 6 hours. So you're giving it you're training the model to learn the map between the state of the atmosphere at some time t, and then it's going to forecast 6 hours into the future. We also fine-tune the model. So basically, what we need to do is that we need the model to learn to predict with its output as its input, right? So after we are done training the model with over a single pass, where we train it to forecast a single step ahead into the future, we train it to we refine these predictions over 2 steps into the future. So basically, in this case, the model, as you see in panel B up on the figure, the model generates a single forecast at time t plus 1 or t plus delta t, and then uses that as the input to itself, and then generates another forecast output, and then you basically create a loss on both of these time steps, and then backpropagate. We also have a precipitation model. I'm not going to go into the details of this right now, but the precipitation field is a very sparse and rather difficult field to forecast. So we need to actually have separated into 2 different models, where you have a backbone model, which is forecasting a lot of prognostic variables, such as the wind velocities, temperatures, and pressures, and geopotential heights, whereas the precipitation is just being diagnosed from the output of the backbone model. So as shown in figure C. And then in the inference mode, you basically just do autoregressive prediction, where you forecast a single step, like 6 hours into the future, feed that back, the model feeds that back to itself, then forecast another six hours into the future, and so on and so forth. So you're stacking these 6-hour predictions on top of each other in order to create a long forecast time series. And we call this surrogate modeling framework ForecastNet. So yeah, I mean, it takes a huge amount of computational power to train. So the training is performed using some really state-of-the-art NVIDIA A100 GPUs. We used at several points of time 256 GPUs for over 8 hours to train the model using a distributed data parallel approach. We were lucky enough to have the new Perlmutter HPC system at NERSC to train this model on. And it does highlight the computational cost of training large, purely data-driven models. So here's a sample forecast output from the model. So I'm just going to play this GIF. So what we're seeing here is the predicted 10-meter wind speed, which is basically we're forecasting U10 and V10, and the top panel is showing the prediction made by our model, almost 120 hours into the future, basically. And the bottom panel is showing you the ground truth, or the true wind speed at that corresponding time step. And it's giving us really remarkable predictions for the surface wind speed. I mean, visually, you can see that they're really close to each other, and this is a purely data-driven model. It knows nothing about the physics or the dynamics of numerical weather modeling. It just has a lot of other prognostic variables that it can actually rely on to learn these fields, but it's all fully data-driven, which is great. And there's another interesting thing. This is actually an old result from a couple of months ago. I mean, we have improved this so far, but I haven't had time to make nice graphics yet. But I'm going to try to play this. Let's see if we can actually play this. So yeah, this is a forecast that was sort of initialized around the time that on T0 is on October 4th, 2016, which is around the time when there was a hurricane approaching the eastern seaboard of the United States. Called Hurricane Matthew, and you can see that you can see the hurricane track very clearly in the predicted 10-meter wind speed, and you can see that the hurricane is moving closer and closer towards the eastern coast of the United States. That's a really neat result. And then there's also like other things that we can get. So one of the variables that we forecast in our prognostic model is the total column of water vapor. And something you might know is that there's these phenomena called atmospheric rivers. And these are columns of moisture that are transported by circulation currents and carry large amounts of water from the tropics to extratropical regions. So large atmospheric rivers can cause extreme precipitation upon landfall with the potential to cause flooding and extensive damage. And some of the more moderately sized atmospheric rivers are often crucial to the water supply of the Western US. So basically forecasting atmospheric rivers and their landfall locations is crucial for early warning and for water resource planning. That's one of the things that's pretty nicely forecast using our total column of water vapor field. If you can see in this region, that's the western coast of the United States, and this is a column of water vapor heading up from the tropical regions towards and making landfall on the California coast. And again, the top panel is the forecast, and the bottom panel is the ground truth. The units are arbitrary, but what's interesting is that we get a pretty good forecast even up to 170 hours, I would say. In general, the forecast net predictions are very, the question is basically how accurate are these ML model predictions compared to an operational numerical weather prediction model. And in general, what we find is that the forecast predictions are pretty competitive with the integrated forecasting system called the IFS, which is an operational ECMWF model. Our purely data-driven model achieves ACC and RMSE, which is comparable, still about 48 hours less, but or at shorter lead times, we actually outperform the IFS models for some key variables. And this accuracy was achieved only using part of the full variable set available to the IFS model. And we do this at a fraction of the compute cost at inference time, although we do require a lot of compute resources for training. Here are some of the ACC and RMSE metrics that we use to compare the IFS and ML model forecasts, basically. So, in each of the cases, if you can look at, let's say, look at U10, which is the meridional wind velocity, you see that the IFS model is about 48 hours better than our model, maybe 50 hours better than our model. For Z500, which is the geopotential at 500 HPA height, 500 HPA level, again, we are only about 48 or 50 hours behind. And then for total precipitation, which is a pretty difficult field to forecast, in some cases, we do outperform the IFS model. These are pretty nice results, and we are hoping to sort of keep improving upon these results.
What does the shading indicate?
It's basically error bars. These are computed over several initial conditions. So all of these are computed over between 30 and 100 initial conditions, depending on some decorrelation.
Not spatial average. So
no,
they're just showing Z500 at one location. Then is this, or is it?
No. These are this is over the entire globe. Yeah.
So the shading includes averaging over the globe.
No,
not.
The shading shows you the error bars that are between the first and the third quartile of forecasts over many different initial conditions, basically. So it indicates some sort of uncertainty between.
Right, but that does not include the spatial uncertainty. So there is a spatial variability.
No, these are globally average RMSEs.
Oh, I see.
Okay. This is another sort of case study that's basically there was this Category 5 hurricane that made landfall in Florida, causing a lot of damage. So it started as a tropical depression on October 7th, 2018, and within a day it had intensified into a hurricane. And after undergoing rapid intensification in the Gulf of Mexico, it reached Category 5 status and soon made landfall in Florida. So within a period of 72 hours, it went from a tropical depression to a Category 5 hurricane to landfall. And what we see is that the hurricane itself and the forecast is captured really well in our 850 HPA level wind speeds. So this is the initial condition on the left, and the forecast net predictions on the top 4 panels with the corresponding ground truth, and we see that we are able to capture the track of the hurricane pretty well. And I mean, we also did some sort of studies on uncertainty. So basically, we can initialize a large ensemble of forecasts because it's really cheap to calculate these forecasts on with a machine learning model. So you can just initialize 100 forecasts, which is pretty difficult to do with a numerical model. And we find that at least for this hurricane, we find that the true path of the hurricane was well within the uncertainty cone of the forecast net forecast, as well as the minimum pressure, the intensification as calculated by the minimum pressure at the eye of the hurricane is pretty well captured by the forecast net model. This is for a lead time of about almost 96 hours. So all of this sort of leads to the sort of broader question as to why use ML at all. I mean, physics-based numerical models perform really well. And machine learning takes a large amount of computational resources and time to train. So why would you bother creating these machine learning based surrogate models at all? So I think one of the key advantages of a deep learning model as opposed to a traditional NWP model is the speed of generating a forecast. I mean, what we estimate is that our ML model is about 100,000 times faster than a traditional NWP model. Now it's difficult to do these apples to oranges comparisons because these ML models are run on GPUs. Typically, numerical weather prediction models are run on parallel banks of CPUs. So it's a really difficult apples to oranges comparison, but there's no question that it's a significant speed up using a machine learning model as compared to an NWP. So in the inference time for a single forecast on GPU is really fast, and you can create an ensemble of initial conditions and you can fold it into the batch dimension on a tensor, and as such inference on a really large batch of even thousands of initial conditions using just a single GPU. I mean, some of these forecasts have been the inference has been done on a single GPU. I mean, you take banks of GPUs to train it, but the inference itself can be done on a single GPU, and this is pretty easy to set up and highly computationally efficient. So this sort of 4 to 5 orders of magnitude speed up over traditional NWP has important implications. So, fast generation of large ensembles of hundreds or thousands of members, which might enable estimation of uncertainties in extremes with higher confidence and current NWP ensembles that, at most you can run 50 members due to the high computational costs. And you might be able to generate cheap forecasts for rapid assessments of high impact weather events. And this also has important implications for the wind energy industry. You can do rapid forecasting of wind fields to allow for disaster mitigation in extreme winds, and you can decide to turn on or off your wind farm based on and mitigate some of these wind power output fluctuations, improving robustness and reliability of wind farms. And so, it's also sort of worth mentioning that it's really cost effective to generate the deep learning forecasts on a commercially available cloud computing hardware. So we try to estimate this using AWS EC2 pricing catalogs. We didn't use AWS for training our model. We used Perlmutter and Selene clusters, but just for giving a rough cost estimate. So a single forecast on an A100 EC2 instance on AWS would cost about 0.00082 USD. 100 member ensemble would cost about 8.2 cents, and computing such a forecast twice daily for a year would be only $60, which is remarkable. I mean, that's a lot of that's really cheap to run. I mean, this does not include the cost of training, of course, but you don't need to train the model very frequently. I mean, at most you would train it maybe a few times a year or a few times a month. Of course, this has several limitations, and it's important to discuss some of these limitations in a lot of detail. So, NWP models such as the IFS model generate forecasts that are provably physically consistent. Our deep learning model in its current iteration does not impose any physics constraints, so we can't really guarantee that the model will generate physically consistent results. The IFS model or most NWP models basically output an order of magnitude more variables at as many as 150 vertical levels sometimes. And notably, the IFS model is more accurate than the deep learning model that we've developed. Although in several variables, the deep learning model approaches the accuracy of the IFS model and exceeds it for precipitation in certain cases. So while we're competitive with the IFS model, we're not quite there yet, and there's a lot more work and research that needs to be done for deep learning models to actually become better than traditional NWP models. And finally, and sort of perhaps the most importantly in this context of just this limited, the work that I presented today, the initial condition for running the deep learning models comes from the output of a past IFS model. So basically, this is a data simulation. The initial condition is generated by the IFS model using data simulation and observational data. So like at this stage, the deep learning model is not able to perform the data simulation part of the task, but we do expect that this will likely change in the future. So with some more research, and we hope some of this work inspires sort of more research in the direction of a deep learning model that performs both the forecasting and data simulation steps. Yeah, so this is purely data-driven modeling. And I'm going to briefly touch upon data-assisted forecasting, but I'm not going to talk too much about it. But, so basically, even with parallelization, as we've seen, if the system is very complex, a purely data-driven model may require a prohibitive amount of training data or computational resources. But if you have partial knowledge of the dynamics, it can give you an imperfect physics-based model. And you can combine that with machine learning to give you sort of a hybrid data-assisted model that combines both machine learning and a knowledge-based model. And this is a basic schematic for that. You have a low-cost or inaccurate physics-based model, which is corrected by using machine learning. And this was, we did this sort of way back in 2018 just for simple toy models. And this could be a way around some data availability and computational resource constraints for building something that's even better than operational NWP models. But this work is still sort of in its infancy, where there's some really nice work that was put out by some of my colleagues and my collaborators who led this project, where they use this again a very low cost general circulation model and then corrected it using ML. And what they found was that a hybrid model that combines a physics-based numerical model of the atmosphere with machine learning produces more accurate forecasts of than the host GCM for the first 7 to 8 forecast days. I mean, this work was still done on a low-resolution data set with a simple, a very simplified circulation model. So it's still in early stages, but yeah, I'm really interested to see where this leads. Yeah, and sort of in conclusion, the role of machine learning may not be as a direct replacement for physics-based models, but ML working in conjunction with physics-based numerical models is a very promising area for research. And yeah, the role of ML may turn out to be the most promising in performing a lot of auxiliary functions such as ensemble generation for uncertainty quantification and data assimilation, or to assist physics-based numerical solvers and to reduce computational cost or improve accuracy. Yeah, I want to thank a lot of all my collaborators. A lot of people have worked on several of these projects that I presented today. So yeah, there's a really, really long list to go through one by one, but yeah, thanks to everyone who worked on this with me. And yeah, we look forward to future work. Any questions?
Thank you very much, Jaideep. I think there should be a fair amount of questions, but you should have predicted all of them by now.
Yeah.
Neelima?
Yeah. See, Jaideep, your knowledge incorporates, your model incorporates some dynamical information, right? So, can it say anything about the trajectory of the cycle? Which way is it going? Where will it go landfall? That kind of thing.
Yeah, I mean, so what we found out from some of our experiments are that, we are able to sort of, what this does is that it's for showing you the trajectory of this particular hurricane. And the way we calculate this trajectory is that the model forecasts the mean sea level pressure, and we compute the minimum or the minima of the mean sea level pressure. And that's typically the eye of the hurricane is where the lowest pressure is. And what we find is that the trajectory that our model predicts, so by basically we run a 100-member ensemble of this model, and then while it's not the exact same trajectory as, we seem to be missing landfall by about 70 miles or so. I mean, which is not too bad considering it's a purely data-driven model and doesn't know much about anything at all, basically, other than the data that it's seen, and doesn't know anything about the laws of physics. I mean, it's still being able to forecast within 70 miles where the hurricane's going to make landfall. I mean, would I trust this model today to tell me accurately where the hurricane is going to make landfall? I probably wouldn't, but I think this is still a nascent field, and these models hopefully will keep getting better and better.
Also, changes of trajectory. Sometimes at least the European cyclones, they just tend to suddenly veer off the trajectory. Yeah,
definitely, and some of those things. I mean. Certainly. I mean, I think that there's also the question of resolution, right? I mean, we train on really high resolution data, which is like a 1/4 degree, but that's still not enough to like actually say we can forecast hurricanes, right? I mean, you need to go like even higher resolution. You need to resolve a lot more processes to actually have a hurricane model.
Jaideep, you use these hybrid models where you have physics-based input into your into the predictions and so on. How approximate is the physics?
Yeah, I mean, it depends, right? I mean, a lot of the hybrid approaches, I mean, these have been done with toy models. So, I mean, you can basically turn knobs and make it as inaccurate or as accurate as you want to, but I mean the concept has been sort of extended.
My question is let me be more precise. Supposing you used a linear physics model when the system is manifestly nonlinear. I mean, that's also a toy model. It's also an approximation and so on. So you get the point, right?
I do get the point. And I think the reason you wouldn't really want to use a linear model is because it doesn't really help you much, because machine learning models, I mean, machine learning is really good at learning linear functions, right? I mean, you would just let the ML model learn the linear model if you could. I mean, so you basically want to give it something of a manifold on which to learn. So basically, if you're talking about like a simple chaotic system, right? I mean, if you could give it an approximation of the manifold on which the trajectory is going to lie, and then add to that some nonlinearities that you haven't been able to model somehow, then that's probably the best scenario to use a hybrid model. But yeah.
Okay. Other questions? Thank you very much for a very, very interesting talk, Jaideep, and it certainly seemed extremely powerful. And 70 miles is good enough for me. I'm packing my bags already. If one has even that level of approximation, it's good to know. And also thank you for also telling us where the directions are moving. I presume that some of this stuff which is unpublished really points to the directions in which the research is going.
Yeah, I mean, we should be coming out with a preprint soon with some of this the unpublished work, most likely in the next few days, actually.
All right. Well, thank you very much.